Welcome everyone to the first session of Statistical Thinking for Forensic Practitioners, a CSAFE Fall 2022 short course sponsored by NIST. Your world-renowned speaker today needs no introduction, but absolutely deserves one. Hal Stern is the Provost and Executive Vice Chancellor and the Chancellor's Professor in the Department of Statistics at the University of California, Irvine. Hal is also a co-director here at CSAFE and is a phenomenal educator that you will be treated to today and next week and the week after that and the week after that. Hal, let's get started.
Welcome, everyone. I appreciate the introduction from Anthony. As he indicates, this is a new offering of an old short course, the Statistical Thinking for Forensic Practitioners. So I'm going to do a teeny bit of introduction, then we'll do a little bit of demographics, find out who's listening, and really launch into the course. But I'm going to take a couple of minutes here, allow for a few more people to arrive if they are so inclined. So why this short course? There have been a few developments over the last 15 years or so that make it an opportune time to think about probability and statistics in forensic science. The first of those is the National Academies of Science report, the Strengthening Forensic Science in the US. And its successor, maybe 7 years later, the PCAST report. And both of those, some controversy, but both of them made the case that more science, more studies would benefit the field of forensic science. A couple of developments following that. One is the organization of the OSAC, the Organization of Scientific Area Committees for Forensic Science, which is run by NIST and has subcommittees for each discipline that's trying to standardize practices. And the other is CSAFE, the center of which I am a part, also funded by NIST as a center of excellence to work with NIST on statistical tools for forensic evidence. The Dalbert standard governs admission of scientific testimony for federal courts. The short version of it for me is that it sets the judge up as the gatekeeper and identifies a number of relevant factors that ought to be considered in deciding whether to accept scientific testimony. So there are several phrases that pop up in the Federal Rules of Evidence, Section 702. One is requiring testimony to be based on sufficient facts or data, that it use reliable principles and methods, and things like that. And for me, and I think for the community of forensic science, one of the things that all of this context, the reports, the Dalbert ruling, the Federal Rules of Evidence point to is that a solid understanding of probability and statistics would be helpful for thinking about some of the issues in forensic science. So that's kind of what leads us to this course. Now, forensic science, as you know, at least as well as I, probably better than I, is a very broad area. So there are a lot of types of questions that forensic scientists deal with. I'm going to focus in on really only one question in most of what I talk about, which can be described as kind of the source evaluation or the source assessment question. So we think about having two evidence samples, one from the crime scene and one from the suspect, and ask whether they come from the same source. During the course of the 4 weeks, we'll see a lot of different examples, a teeny bit of DNA, some discussion of trace evidence like glass fragments, and then the primary discussion is around pattern evidence. So this is a new outline for the course. I've tried to change a couple of things. The reasons for the changes, by the way, I've done this course many times, and a common bit of feedback that we get is positive feelings, but also a sense of things being maybe a little rushed and not enough time. So we thought it would be a good experiment to try and space it out a little bit. One thing you should know with professors is if you give them more time, they just talk more. So it's not clear that there'll be a lot more free time, but I will try to make sure we have time for questions. I really would like to engage with the audience in that way. So please do use the Q&A feature to throw any questions out there as they come up. I won't necessarily answer them right away, but I will periodically stop and look and go over them. So here's a brief outline for the course. Part one is relatively unchanged from what I've done in the past, cut a few slides, but it's a focus on probability and how it relates to forensic science. The rest is changed quite a bit. Part two, next Friday, will focus on collecting data, thinking about topics like reliability, validity, accuracy, and then talk a bit about black box studies under a heading that I call Forensic Evidence as Expert Opinion. Part three will introduce some of the more statistical concepts. For those of you who had an undergraduate statistics course, part three is most likely to cause flashbacks and discomfort. But I'm going to teach some of the statistical methods, not as a statistics course, but as they are relevant to what's sometimes called the two-stage approach to analyzing evidence. And part four is to review some of the ongoing conversations in the community about the likelihood ratio. And so that's what we'll get at over the next 4 weeks. I hope that you're able to make all of those. Let me stop here and pause for an instant and ask the admin team to put up a Zoom poll. So this will give us a chance to see how Zoom poll is on some of the demographics. Who's here? What do you do? What disciplines do you study? So there you go. There's 3 questions here. One is, where are you joining us from? The second is, what is your profession, student, educator? And the third is, if you're a practitioner, what areas do you focus on? This is a good Zoom practice too. The first question will only accept one answer. The second and third will take multiple. So I'm going to wait a minute, give you a chance to do that. And I do ask that you fill out the Zoom polls. We'll use them throughout the course to check on concepts and the like. And it's a lot more fun for me, and I hope for all of you, if we get a chance to check in together, and I can use that to reinforce some of the points where maybe people are not understanding. So here's the answers. The majority coming from the East Coast, which is good because it's a decent hour there. It's a little early out here on the West Coast. We have most of the people, not surprisingly, from in the US, but a few from Europe and a few from somewhere more exciting than Europe. Unfortunately, we don't ask where that might be. The large majority, as is the intent, are forensic practitioners, a couple of students as well. And in terms of disciplines, majority on physics and patterns, some chemists, and a few digital media and crime scene examiners. So thank you for answering the questions. And now on with the show. The first part, as I mentioned, is focused on probability. So things that I hope that I can convey over the next hour and 50 minutes. What is the difference between a population of objects in a sample, and how does probability fit into that? Understanding how probability is defined and how it's used. And then we get into some of the more specific context for probability concepts that show up frequently in forensic statistics, conditional probability, independence, Bayes' theorem. So today's presentation, I'm going to actually motivate with 2 case courses. Two court cases, easy for you to say, easy for me to say, 2 court cases. The first, very famous, if dated, is the People of California versus Collins. It's a case based on a robbery that took place. An elderly woman was attacked from behind and robbed. There's some eyewitness testimony, both from the victim and other witnesses. They described a woman with blonde hair and a ponytail, a yellow car driven by a black man with a mustache and beard. Police did find a couple matching that description, and they were arrested. During the court case, the prosecutor called as an expert witness a mathematician, and what the prosecutor did is told the mathematician that the frequency of the various traits that the eyewitnesses had observed. So that, for example, the chances of seeing a yellow car was 1 out of 10. The chances of seeing a white woman with blonde hair is maybe 1 out of 3. A woman with a ponytail, 1 out of 10, and so on. And then the prosecutor asked the mathematics professor, the expert witness, to go through some of the rules of probability. And in particular, there is a rule that we will cover a little bit later that says if you have independent events, such as, the woman is the yellow car is involved in the case and the blonde woman, that you can multiply the probabilities to get the probability of multiple things happening. And so the witness did that and found in this case, the probability that a couple would be found to match all of the eyewitness testimony was about 1 in 12 million. The prosecutor turned to the jury and said a couple that matches all of these observations is so rare, 1 in 12 million, that clearly the couple on trial must be the couple that committed the robbery. So that's the background for why I think thinking about probability. This is one of my favorite pictures. That's probably a sign that I don't appreciate good art. But what the picture is intended to show is how statisticians think about the world. That is, there is some population we're interested in. We use the word population. It may refer to people, but it may refer to other items as well. It could refer to all manufactured footwear. If we had footwear evidence, it could correspond to a suitcase full of little bags of white powder in a drug case that we might be working on. So the population is the entirety of the set of objects that we are interested in. But it's frequently not realistic to collect data on the entire population. Certainly, if we think of the population as all potential voters in the United States, that's hundreds of millions of people, and we wouldn't be able to collect data on them. So we frequently take a sample. And the way that I think about some of the key concepts is that the laws of probability is most helpful for us in if we know something about the population, we can tell you about what you're likely to find in the sample. And so that's the top arrow. And statistics is the field that says, here's what I've seen in a sample, and here's what that allows me to infer about the population. So as we will see over the course of the 4 weeks, this picture will come up more than once. We use it both ways. If we know something about the population, we can say something about the sample. If we know something about the sample, we can say something about the population. I mentioned a few of these in defining the terms. The population might be 100 bags of white powder in a suitcase. And then in that case, the sample would be a small subset that we choose to analyze chemically. One of the examples we'll use over the course of the 4 weeks is a glass fragment in a case where maybe there's a broken window at a crime scene and a suspect is found and there are glass fragments on the suspect. So we might take, in this case, there to be 2 populations, 2 glass populations, one the glass at the crime scene, the other the glass on the suspect. Again, we'd be unlikely to analyze all of the glass. We'd take a few fragments from the crime scene, we take a few fragments from the suspect, and we'd analyze those. So those are a couple of examples that will come up as we talk through the course. A key concept that will come up for us as we do this is that we will typically have measurements, repeated measurements from samples. And we're going to be interested a great deal in studying the variation in those measures. That is, the 2 types of questions statisticians want to ask is, how much variation might I see in a latent print from a given finger if I took repeated impressions? And how much variation would I see if I took impressions from different fingers? Right? Those turn out to be key concepts. So on to the meat of today's session. What is probability? So probability is the mathematical language that we use to talk about uncertain events. A probability is a number between 0 and 1, describing the likelihood that some event occurs. What do I mean by events? Almost anything counts as an event. In the forensic world, an event could be, what's the probability that I measure a fragment of glass and I get a refractive index between 1.52 and 1.53? What's the probability a randomly chosen finger has a loop pattern? What's the probability that the crime scene evidence and the suspect evidence have a common source? So probability in concept can be used for any of those, as well as myriad other questions. As we do this, the baseball playoffs have just started. So one can imagine asking, what's the probability the Yankees win the World Series? Or what's the probability the Dodgers beat the Padres tonight in a single game? So for me, probability is very broad. Cloudy day here in Southern California. What's the probability of measurable rain today, right? And we will use minimal, but some mathematical notation during the course. So at the bottom here, I have the kinds of things that I might write down. I might use the letters PR for probability, and PR parentheses E is the probability for the event E. And sometimes we'll talk about the probability that E doesn't occur. And so there's some ways we'll talk about that, but I will try to minimize the use of notation. Probabilities, numbers between 0 and 1. We sometimes use them as percent. And so if you watch the weather forecast, they will tell you there's a 40% chance of rain. That's just another way of saying that the probability of rain is 0.4. The two endpoints for probabilities have special meaning. If something has probability 0, that would be an event that we would say can never happen. If an event has probability 1, we would say that the event is absolutely sure to happen. One of the jokes people make about statisticians is that being a statistician means never having to say you're certain. And that's because statisticians very rarely say that something has probability 1, just because even if it's happened every day, in the last, millennia, the sun has come up every day. What's the probability that the sun will come up tomorrow? And no, I'm not going to sing, so don't worry about that. So many people say the probability the sun comes up tomorrow is 1. Most statisticians would say it's very, very high, but it's probably not 1, right? We do sometimes say that an event has probability 0 if it is just an impossibility for something to happen. So, flipping a coin and having it land exactly on its edge could be said to be probability 0. Whoops. So that's what that's some of the basics of probability. How do we think about probabilities? There are two main interpretations in the world. One is as the long-run frequency. If you've had a probability and statistics course, you've probably learned this interpretation of probability. It clearly applies well in certain settings. We would all agree that the probability of tossing a coin and having it land on showing its head up is around 0.5. Why would we say that? Well, we have typically had some experience flipping coins or seeing someone else flip a coin, and we know that in a long sequence of such flips, we'd get about half heads. The same for rolling a die. We've done that. We play board games. We've seen that. We know that each side of the die has the same value, so we feel pretty good about that. So that's called the long run frequency. It is, I can imagine repeating this experiment or this activity, and I have an idea for what I would see in that long run. So that's the long run frequency interpretation. But there's also the subjective probability. So these are more personal opinions. What's the probability the Angels win the World Series? Well, this year we actually do know that, and the answer is 0. They did not make the playoffs. Excuse me. But we could ask, what's the probability the Yankees win the World Series? We could imagine a long-run frequency. How would that work? I would say to myself, if we played the World Series or the playoffs 100 times, how often do I think the Yankees would win? But that's not super meaningful. So at the end of the day, these probabilities tend to come down to opinion primarily. And so So those are the two main interpretations. Where do probabilities come from? As I said, one place is we may have experience, empirical evidence that flipping coins 100 times yields about 50 heads, which would make the probability 0.5. Sometimes we have mathematical models. I'm a big fan of the website 538. So if you go to 538, they have a mathematical model for the strength of baseball teams, and they have, based on that, a prediction of the probability that the Yankees win the World Series. And I won't tell you now, but I'll tell you soon what that is. So that's another way we sometimes get probability out, is through mathematical models. And the third is sometimes opinion is all we've got. And we give our opinion for how likely something is to happen. And although you may think you don't do that, you do that in various ways and shapes and forms. One example I often use to tell people is, we just got a new car and I had to put it on the insurance policy and I had to choose a deductible. How do you choose a deductible? Well, you can maybe ask your insurance agent, but a deductible is really a probability calculation, because you have to decide how likely it is that you're going to have an accident or a claim above a certain amount. And there are several factors that go into that, but that's a lot of opinion work coming into it. Won't spend much time at all on this slide, but probability is closely related to odds. If anyone here has or is a gambler, has gambled or is a gambler, odds are actually ratios of probabilities. So you can say, what's the odds in favor of the Yankees winning the World Series? And that would be the ratio of the probability they win divided by the probability they lose. And odds are most often given against the event. So we say, how often would they lose? And odds are related to probabilities. And the one way to think about that is the last bullet here, which says, suppose someone says, you can bet on the Yankees, but the odds are 4-1 against, or you can bet on a horse and they're 4-1 against. What that means is, if you bet on the Yankees, you'll win $4 if they win, but you'll lose $1 if they don't win. And for that to make sense, for that to be logical, it implies the probability of them winning must be 0.2, because then 20% of the time you'd win $4, 80% of the time you'd lose $1, and you'll break even in the long run. So odds and probabilities go together. For our purposes in this short course, we'll talk primarily about probability. If you've had a course, you may have had an unpleasant experience with probability. Why? Probability results can be confusing, in part because a subtle change in how you word the question can lead to a big difference in the answer. And there are lots of examples of this. I'm going to talk about one today, but I'm going to leave you with another one that you can look up if you like. There's a problem called the Monty Hall problem, based on the TV game show The Price is Right. Monty Hall was the first host of that game show. He is no longer the host of the game show. But it's a very interesting problem that has a fun history. So if you have any interest after today's short course, encourage you to look at the Monty Hall problem. But I'm going to work on a different one called the birthday problem. And so before I do that, I just want to give you my takeaway, which is, though probability can be confusing, and the question I'm about to ask you is a prime example, they really are key concepts. So don't get discouraged. Probability is very important to life and to forensics. And we're going to spend some time today trying to become more comfortable with it. So here's the birthday problem for you. Suppose there are 50 people in a room. What do you think the probability is that at least 2 of those 50 people share a birthday? And there are 4 choices. 2 things. One, I have to confess, the answer is ahead on the next slide, so please don't cheat and look at it. And so now I'll ask Kristen to put up the Zoom poll and give you a chance to think about it, and then we'll talk it through. Okay, Kristen, here we go. So the largest number, the plurality, say 15%, And then we have people all across the board. And kudos to the 6 people who participated. First of all, I should say, bad for the 8 people who did not participate. Then kudos to the 6 people who got the correct answer, which remarkably, I think, and I'm a professional, is 0.95. It's really quite surprising. We don't necessarily want to take the amount of time it would take to argue through it, but I will argue briefly. The reason that most people say 0.15 is it's really the first thing you think of when you look at it, which is, there are 365 days in the year, 366 in leap years. And so you think, okay, if I pick a day and I take 50 chances, it's about 50 out of 365, which would be about 0.15. That's not quite right. And the reason, the short intuitive reason is, it's not one day that we're worried about. We are thinking about all possible comparisons. So you can imagine taking each of the 50 people and comparing them to each of the others. And so I have A versus B and A versus C and B versus C. And so you get a lot of pairs that could be the matching pair. That proof doesn't really work, but that gives you an idea about why it's more than 0.15. The detailed argument is at the bottom of the slide. And rather than walk through it, I will give you the following thought processes. If you think about having a calendar rolled out on the ground, so you can see 365 spots like at a roulette table, and you say, okay, first person walks into the room, puts a coin down on their birthday. They can put it anywhere, so that's easy. Next person comes in, they can only put it on 364 out of 365 spots. And then the next person, if we're going to not have matching birthday, can only put it in 363. And those seem easy to do. But by the time you get to the 50th person, they're a little bit more constrained. They can only put it down in about 85% of the spots. And when you end up multiplying all those together, which turns out to be the right thing to do, it gets really, really small. And so it's almost certain that in a room of 50 people, that you'll find 2 matching birthdays. Really quite remarkable. You can try that at your workplace if you like. With 23 people is about the break-even point. At 23 people, it's more likely than not. So fun problem, I hope. Opportunity to win some money at a bar if you like. So that's the basics of probability. It turns out that the most key concept in applying probability to forensics, I would argue, is the notion of conditional probability. So what is conditional probability? To answer that, I'm going to change to a specific context. This example comes from one time when I was giving this course in New York, and I had to fly across country to give it. And so the day before I was flying, I said, gee, I wonder how likely it is that I'm going to get delayed during this trip. I was taking a nonstop from LA to JFK. And American Airlines, which I was taking at the time, actually has data when you make the reservation that shows you the history of the flight, how frequently it had been delayed. And based on that data, it suggested the probability of delay was about 27%. But one of the reasons I started looking into this was that the weather forecast was calling for rain showers in New York. And I wonder if that made it more likely to be delayed. Unfortunately, I couldn't find a lot of data about that, but I did want to walk through how to think about it. And so that to me leads to the notion of conditional probability. And conditional probability gets written down with a vertical bar. I hope you can see my hand pointing at the vertical bar here. And we read this as what's the probability of a delay given that there are thunderstorms in the forecast. Sometimes we'll say conditional on thunderstorms in the forecast. Sometimes we'll say, in the most drawn out way, what's the probability of a delay, flight delay, given the condition that there are thunderstorms? So that's why we think of it as conditional probability. Let me just see, there's a question, so I want to kind of see what the question is. Good question, Stephanie. I'll come back to that. Okay. So to talk about probability in this way, I'm going to go back to my favorite picture. Okay. So how does probability work in this picture? For me, the way that this works is the population starts as all flights from LA to New York that have ever occurred, if you will. And on each flight, you can imagine there's a sticker, and the sticker says, this flight delayed, and another one has a flight that says this, another one has a sticker that says this flight is not delayed. So we can think about 1,000, 100,000, however many flights you want to. That becomes the population. And then the probability statement becomes the probability that the flight will be delayed is 27%, because 27% of those flights have stickers that say delay on them. Okay, so that's the basic definition of probability. When we talk about conditional probability, what we're doing is saying, I'm not interested in all of those flights that went from LA to JFK. I'm only interested in the flights that happened on days when there was a forecast for a rain shower. So that is a subpopulation. That's taking a subset of the population and saying, don't worry about the whole population, only work on the subset that happened on days with forecasts of rain showers, and tell me what fraction of those were delayed. And unfortunately, I don't have accurate data for that, but we might imagine that it's higher. And so here I've speculated that, in my opinion, that probability is about 0.5. So conditional probability changes the information that we have and changes the population we're talking about. So when we talk about conditional probability, we talk about what's the event I'm assigning probability to. In this case, I'm assigning probability to the event that my flight is delayed. And the second part of a conditional probability is, and what information am I assuming that I have? In this case, I'm assuming that I have information about the weather forecast. In this case, you can really think about two different probabilities. One says, assume I have no information other than I'm about to get on a plane from LA to JFK. What's the probability that that plane will be delayed? My guess is 0.27. Second situation, I have more information. It's a rainy day forecast. And I can ask, on those kinds of days, what's the probability? For me, I would say all probability is conditional. All probability depends on what you were assuming about the population. Here's, so let me stop for 1 second before we go too far into conditional probability. Stephanie put in the Q&A, if you're doing the birthday problem, can you think about it the other way than the way I wrote it down? I said, let's think about the probability of not getting matching birthdays. And I said, the first person can be anywhere on the map. The second person can only be in 364 slots. And Stephanie asked, can you do that the opposite way? Can you say, let's let the first person put down their birthday, and they can put it down wherever they want. Well, so actually, Stephanie, I'm going to back up and say, Stephanie said, can you say the first person could put it anywhere? The second person has a probability of matching of 1 in 365. And if they don't match, there are now 2 covered. So the third person can come in and get 2 in 365, and so on and so forth. Can you build it up that way? The answer is yes, but I hate when people answer questions, yes, but. In this case, the answer is yes, but that leads to a much, much more complicated path, because when the second person puts it down, you have to account for either they do match or they don't. And so you have to go down that path for every person that comes along. So it turns out to be a much harder way to keep track than the way I laid it out. But I do appreciate you answering that, you asking that question. Okay. I can't get it off the screen. There you go. Sorry about that. So again, back to conditional probability. Here's an example, and this is an example of based on an article that was published about the death penalty. And it looked at the sentencing of 362 African American who were convicted of murder in Georgia during the 1980s. So old data. Found in looking at those cases that 59 of the 362 men were sentenced to death. And the authors of that study were looking at the role that the race of the victim might play. And so they created what's often called a 2x2 table. This is a 2x2 table. Why do we call it a 2x2 table? It has 2 rows and 2 columns. It actually, if we're a stickler, has 3 rows and 3 columns because there's a total row and a total column. But the meat of the table is this 2x2 box in the middle. There are 2 rows. Was the victim of the murder white, or was the victim of the murder black? And then there are 2 columns. Was the convicted murderer in the case given the death penalty or no death penalty? So every case that these researchers studied falls into one of these 4 cells in this 2x2 table. So there were 45 of the 362 cases in which the victim was white and the murderer got the death penalty, and so on and so forth. And then I add the totals to interpret the table. So one way that we can think about probability in this setting is to think about these 362 as the population we're interested in. And then we can ask various probability questions. What's the probability that a convicted murderer in Georgia received the death penalty? Well, there are 362 cases. I'm going to pick one at random. 59 of them had the death penalty. And so the probability that I would pick a case that got the death penalty is 59 out of 362, or 16%. So that's out of the total population. So how does conditional probability work in this case? I've repeated the table here, and now I'm asking you a question. Suppose we focus only on crimes in which the victim was white. What's the probability that the convicted murderer received the death penalty in that case? To me, this would be a conditional probability calculation. What is the probability that a murderer got the death penalty if the victim was white, or given that we know the victim was white? So let me give you a little bit of time to look at that. Okay. So you'll notice the 4 answers that I gave are just different ways of slicing up the data, and participation up to 42 people. Thank you very much. Really appreciate that. The majority think the answer is 45 out of 130, or 35%. And so let's go forward one slide. This is an example of conditional probability. Why? My question has restricted our attention to a subset of the population, only the 130 cases in which the victim was white. And in those 130 cases, the first row of the table where the victim was white, the death penalty was 45 of those cases. So the correct answer is the cases where there's a white victim and the death penalty, 45, divided by all of the cases where the victim was white, 130, and the conditional probability is at 35%. So it was 16% in the full population, 35% in the subpopulation of interest. You can see in this case that the victim's race matters a great deal in whether death penalty got assigned in these cases. The overall rate of 16% was really a combination of 2 scenarios. An important thing to note, and this will come up in some of the forensic examples that we think about, there are other factors too. So this, I have not yet told you about the context for the murder. And the death penalty might be more likely in some kinds of murder cases than others, right? The aggravating circumstances and the like. So we don't necessarily know for sure that the white victim is the only factor that matters. But what we've seen here is that the race of the victim seems to have an impact on the probability of the death penalty being assigned. So, so that's conditional probability. There's a question, so I want to see what that is. Oops, I didn't get rid of the question. Good. Okay, here's more forensic-based example of the kind that we're interested in when we think about pattern evidence. This comes from a thesis done by a student at the University of Central Oklahoma, where they were able to collect data on a set of bullet groove impressions from 9mm bullets, and look for the number of consecutive matching stria. And they did 206 pairs of paired comparisons. 146 of them were in cases where the two impressions were known to come from the same bullet. And there were 60 impressions where the two impressions were from non-matching bullets. And the student actually did the microscopy and recorded the maximum number of consecutive matching stria and recorded the data in a table here. And so here, each number in the table records for either the known match case or the known non-match case, the number of consecutive matching stria. There were 23 examples in which it was a known matching pair, and the consecutive matching stria, the largest consecutive matching stria was 4. So how might we use a table like this? Again, the overall probability of seeing a large number of consecutive matching stria is relatively small, but we might be interested in how that differs for known matches and known non-matches. And so suppose we decide 5 or more consecutive matching stria is unusual and might be thought of as evidence for same source. Note that when the pair is a known match is 14, 11 plus 2 plus 1 out of 146, or about 10%. Whereas the probability of 5 or more matching stria, given that they come from non-matching pairs, is 0 out of 60. So this is why conditional probability will turn out to be important for us. We might be interested in how a measurement that we can make behaves in different assumptions about the world. I'll also note here, there are 2 different ways of doing conditional probability. The 2 examples I gave work by thinking about each row separately, but we can also think about each column separately. So maybe I want to say, let's consider all of the instances in which I saw 4 matching stria. What fraction of those were known matches? And in this case, you would find out that the probability of a known match given a consecutive matching stria is 4 is 23 out of 24, or 96%. I mentioned at the start, probability is sometimes confusing. This is an example, right? There are 2 different ways of doing conditional probability in this table. One way is to say, let's think about one of the rows, known matches, and think about that subpopulation of cases, and think about, and then look at CMS in those cases. The second way, the last bullet, no pun intended on this slide, is focusing instead on a column and saying, I've done the analysis, I saw 4 matching stria. What can you tell me about cases with 4 matching stria? So it's very important that we think about what event are we assigning probability to, and what event are we assuming we know something about. One of the things that's especially interesting here is the last item seems like it might be interesting to us. We might be interested in saying, oh, I saw 4 consecutive matching stria. That only seems to happen with known matches, and therefore I should call this a known match. That's a perfectly logical argument, but it turns out that there is a complication with that argument, which is that answer turns out it will depend on how many known matches and how many known non-matches the thesis student ended up looking at. So if the study was redone, but Mr. Lee used, 6,000 non-matches and 146 matches, it's quite likely that they would have seen more 4s in the non-match pool. And so that would change that last answer. And so it's going to be very important that we think carefully about which information does it make sense to think about having fixed. So more on that as we go on. Let me check in a new question. Will we be able to get copies of the slides after each session? The answer to that is yes. Not only that, though, you should have gotten these slides before the session. Kristen, do we know if these got sent out before? Paging Kristen. For now, let me just say, yes, we will send these out. I thought they were going out in advance, and that will be what we try to do for the next few weeks of the course. I apologize that they did not go out before. So I don't seem to be able to dismiss the questions. There we go. Dismissed 1, dismissed 2. Good. So thank you for asking that. I'm going to ask our administrative team that's on with me to look into whether they were sent, whether they can be sent to all the registered people now, or whether that will have to wait until we are done. So thank you for bringing that to my attention. So a few more things to say about conditional probability. Sometimes the additional information doesn't change the probability of an event. And in fact, if you have seen a statistics course, one of the reasons that we use coin flips and dice rolls in examples is not because they're super important in the world, but because they are examples where we have independence. So what do I mean by independence? Going back to my flight delay example, I argued that the probability that a flight from LA to New York that would be delayed would be about 27%. And then I got concerned about the impact of a weather forecast. Suppose I change that and I say, I had dinner the night before I flew out. What's the probability the flight's going to be delayed given that I had pasta for dinner the night before? Right. You can ask that question. It just says, let's imagine all possible flights to LA and only focus in on ones that happened on the day after I had pasta for dinner, and look at how many of those got delayed. There's certainly no reason to believe that whether I have pasta or not impacts a flight delay. And so we might imagine that the probability of flight delay, conditional on my having pasta for dinner the night before, is the same as the probability of flight delay in general. And if that's true, we would say the flight delay is independent of what I had for dinner. And so when we do conditional probability, if the additional information I have has no impact on the probability, we say those things are independent. One way that this shows up in forensic science is when they do DNA analyses, the way that they usually do it now is they look at one location on each chromosome and they see, do we match on that one location? They do that because the DNA on independent chromosome, on each chromosome, is independent of what's happening on the other chromosomes. And we will see why independence matters. Sometimes we may want to know about the probability that 2 different events happen. What's the probability my flight is delayed and my luggage gets lost? What's the probability to get ahead on my first coin toss and ahead on my second coin toss? Turns out This is in general a hard problem. Why? The probability of the second event could depend on the first event. As an example, I looked up before the baseball playoffs started, what's the probability that the Yankees would win the World Series? And the estimate on 538.com was 0.15 or 15%. The Yankees, one of the better teams, but baseball turns out is a pretty random sport. There's 3 or 4 good teams, and the estimate was 0.15. But you could ask, what's the probability Yankees win the World Series if their star, Aaron Judge, gets hurt? And we would certainly imagine that that lowers the probability. So the probability assessment that we would make could clearly depend on information that we have. So in general, if you want to know the probability that 2 events occur, there's a natural way to think about it, which is to think about them sequentially. And so we can say, and this is one of the rules of probabilities, the probability that A and B both occur is the probability that A occurs first. And then we ask, what's the probability that B occurs once I know that A has occurred? So we get the conditional probability of B given A. And the same for we could do it the opposite order and ask about B happening and then A given B. But if 2 events are independent, that's a special case. And it turns out that simplifies the world, because knowing that A has happened doesn't change the answer for B. And so we get the simple rule that's known as the multiplication rule for probabilities. This applies, for example, for coin tosses. The probability that I get heads on the first toss is 0.5. The probability that I get heads on the second toss does not depend on the first toss, is still 0.5. And so the probability that I get heads on the first toss and heads on the second toss is 0.5 times 0.5 equal 0.25. Why am I telling you this? I bring us back to the case we started with, the people of California versus Collins. Recall that the expert witness testified that given all of the characteristics in the case, a yellow car, a blonde woman, a black man with a beard and a mustache, if those characteristics are independent, then the probability is obtained by the multiplication rule, and it turns out to be 1 in 12 million. That was the testimony that was given by the math professor. The Collins couple were found guilty in that case, and Malcolm Collins, the man in the couple, appealed, claiming that the probability evidence submitted during the trial was prejudicial to the jury. And so what should the court do in this case? And here are some options for you to think about. The court could let the conviction stand, arguing that the expert is right. They could also let the conviction stand. They could find that Collins is right, the probability is irrelevant, but the eyewitness testimony is enough. They could overturn the conviction, maybe saying there's no basis for those probabilities. They could overturn the conviction, saying the assumption of independence is not justified here. Or they could overturn the conviction, saying statistics has no place in the courtroom. In this case, we're gonna put up a survey and allow you to give any of those answers. Pick as many as you think are relevant. So here we go. So we have a lot of answers here because people could answer more than once. The 2 with the most support are both arguing we should overturn the conviction. There is no basis for those probabilities, or overturn the conviction. The assumption of independence is not justified. 2 people think the conviction should stand based on the strength of the expert witness. And one says the conviction should stand because the expert is right. Thankfully, no one said there's statistics has no place in court. I'm glad to hear that. So let me give you my take on all of this, or let me tell you what actually happened. The Collins couple, as I said, were found guilty. Malcolm appealed. The California Supreme Court in this case reversed the conviction. The court really, in my opinion, did a very good job of arguing. They basically argued the 2 things that most of you said, which is there's not really a basis for the probabilities that were specified in court. The prosecutor just read out those numbers without saying where they came from. And then the court also recognized that though the math professor did if they're independent, I can do this, that there had never been an argument made about why we should think about them as independent. Interestingly, the court also said that the prosecutor's use of probability distracted the jury, and so did seem to argue that the mathematics itself did not have a place in court. I did not find that part of the judge's ruling particularly compelling. But so as I tried to elaborate on this for the course, I discovered something shockingly to me, but true. Almost impossible to get data on the frequency of men with mustaches and beards. I wanted to use that as an example because I suspected, correctly as it turns out, that having a mustache and having a beard are not independent. But so it turned out to be really hard to find data, but I did find through the power that is Google, a survey that had been done in France. And in that survey, they found that 47% of the men had a mustache. And they found out also that I think it was 43% of the people, of the men had mustaches and beards. And if you use the rules and the definition of conditional probability, it turns out that the probability of having a beard, given that you have a mustache, is 0.91, whereas the probability that you have a beard in general is about 0.48. And so they are not independent, clearly. In fact, they're very, very dependent. The very large majority of men who have one type of facial hair also have the other type of facial hair. Some of the things may be independent. I don't know whether having a yellow car is independent of being a blonde woman. Maybe they're dependent, maybe they're not. But we know in at least this case, there's some degree of dependence. And the way the laws of probability work is when you multiply probabilities, because all the probabilities are less than one, the numbers get smaller and smaller and smaller. And so assuming independence when it's not true can lead you to believe that the thing is very, very rare when it's not so rare. And so dependencies make the evidence less compelling. And so in my view, the courts were correct in their ruling that the probability introduced was not appropriate. I disagree with the notion that the mathematics was a distraction, because I actually believe calculations like the one that were done are relevant and in fact are now used all the time for DNA evidence. I will say the other thing that the mathematics, the other thing that the court said, which I think is important and interesting, is that the prosecution, by relying so heavily on the mathematical argument, never really gave the jury any guidance on how to think about the possibility of more than one couple, or remember there's also the possibility of disguise and other things. Libby Stern, no relation, notes that the only data I could find was from France, and that may or may not be relevant in a US case, and that's a common limitation on trying to apply probability. And so, we can talk later about what to do in cases like this. But for me, at least, the French data was able to think about the dependence issue in a way that probably does translate well. So we are trying to get better information about the slides. It does seem they did not go out, and I do apologize for that. We will definitely get these out, probably beginning of next week, and get the second set out at the same time, or at least a day or two. I'm still working on the second set, so we'll get those out as well. Libby, thank you for that comment, and I apologize for the one last time about the slides. Okay. So that's the Collins case and the basic introduction to probability. It also introduced some of the concepts related to independence and conditional probability. I Whoa, someone is saying the sound is off. I could use some clarification on this. If you cannot hear me, please write something into the Q&A. Okay. Chris, this seems like it may be a local problem. Sorry. Okay, I'm going to go on, assuming that it's not a global problem. I'm going to go on with a second case that motivates a little bit more thinking about probability. This is the state of Connecticut versus Skipper, and this is a sexual assault case. In this case, the state's expert witness was testifying about genetic testing, paternity testing, and there was a sexual assault. There was a child. The victim of the sexual assault ultimately had a child, and there was a question about whether the accused was the father of the child. And so paternity testing was done. A paternity test is a genetic test. And the expert in the case reported what their software provided as a paternity index. Turns out a paternity index is an example of a likelihood ratio. And the paternity index was 3,496. And the interpretation of that is the probability that the defendant would produce a child with the given genotype when having a child with the woman is 3,496 times as large as the probability that a random other person would produce a child like this with that woman. So that's what the paternity index means. But the expert said, not only can I tell you this likelihood ratio, I can tell you more. I can tell you the probability that this man is the father. And they did so. They said the probability this person is the father is 3,496 divided by 3,497, which is 99.97%. And this person was also convicted and later appealed the case. To understand the statistics in this case, we need to go a little bit further in our discussion of probability to a topic that's known as Bayes' theorem, and to a framework that we will come back to later in the short course for assessing forensic evidence. So go back to the, trying to get rid of this thing on the top of my screen. I'm not sure how to do that. Isn't that supposed to go away at some point? Well, we'll hope it goes away. Okay. So Bayes' theorem, or Bayes' rule, as it's sometimes known, is named for the Reverend Thomas Bayes, an English mathematician, philosopher, and minister. Back in the 1600s, ministers were often the only highly educated people, and so many of them did science and philosophy and other types of research. The Bayes' theorem is, again, we can think about Bayes' theorem in our picture. It's sometimes known as inverse probability because it is a way of going from the sample back up to the population. So I've argued that probability is what tells us to go how we go from a population to a sample. Bayes' rule is the first approach, sometimes known also as Bayesian statistics, for going from the sample back up to the population. To do it, I'm going to try and get rid of these questions and hope that it will get rid of them. It does. Good work, Cal. Okay. I'm going to use a gunshot residue example. And I have to preface the gunshot residue example by saying, this is not really the way that gunshot residue is used. And so I apologize for that. I find it a very helpful and interesting way to introduce the concept. But if you like, you can think about any other kind of diagnostic test. So I will also talk about pregnancy tests. So this is another example of what I mentioned earlier as a 2-by-2 table. The two rows in this case correspond to the truth. Does the individual have gunshot residue on their hands, or do they not have gunshot residue? So that's G, gunshot residue, and not G, no gunshot residue. And across the columns are the test results. So I have a test that does gunshot residue detection. And the first column says the test came back positive. And the second one says the test came back negative. As with the death penalty cases, every time I do one of these tests, I am in one of these four situations. Either the person actually does have gunshot residue and the case came back positive, which is known as a true positive, or the person has gunshot residue and the test came back negative, in which case the diagnostic test has made an error. It has given me a false negative. And similarly, for the case where there is no gunshot residue, I can get a true negative back from the test or a false positive back from the test. And so these are all in the form of conditional probabilities. That is, if the truth is the individual has gunshot residue on their hand and the test comes back positive, that conditional probability is known as the true positive rate or the sensitivity. Similarly, we get a true negative rate or specificity. The test is very specific. If you don't have gunshot residue, it doesn't come back positive. And then we can get the error rates, the false positive rate when I look at cases where there is no gunshot residue and the test comes back positive, and vice versa. Not vice versa, actually. The false negative when there is gunshot residue and the test comes back negative. If you had some statistics, you may be familiar with the notion of a false positive as a type 1 error and a false negative as a type 2 error. I don't believe that's appropriate language in this case. And we'll see that in a subsequent session of the short course. But I won't use that language anymore today. So we'll talk about false positive and false negatives. This setting is really known as the diagnostic testing setting. And so another example where this happens is pregnancy testing, right? A woman may be trying to get pregnant, and so is missing her period, so goes to the drugstore, buys a pregnancy test. Same situation. The woman is either truly pregnant or not. The test result is either positive, you're pregnant, or negative, you're not pregnant. And we have all of the same situation. It turns out when you develop a diagnostic test, a gunshot residue test, or a pregnancy test, you do a lot of research in the lab. And the research you do is you take cases where you know the answer, and you see if your test gives the right answer or not. So in practice, when you buy a pregnancy test, and this is true, it's not a homework assignment, you don't have to go out and buy a pregnancy test, but if you are in the stage of life where you may have bought a pregnancy test or may buy a pregnancy test, I encourage you to read the back of it, or in fact, just sneak into the drugstore and read the back of it. It should be said somewhere in the small print on the back of the test how accurate the test is, and they will tell you they should tell you the false positive rate and the false negative rate. So the challenge with diagnostic tests is the package will tell you the probability that the test comes back positive if you're pregnant. It should tell you the probability that it comes back positive if you're not pregnant, the false positive rate. But that's not what you care about. You take the test comes back positive, and you want to know, can I be sure that I'm really pregnant? Or can I be sure that the person actually has gunshot residue on their hand? This is where Bayes' theorem comes in. Bayes' theorem allows us to flip the conditional probability around. So a couple of things to note here, one of which is there are two different conditional probabilities. If you look at the last bullet on this slide, the probability that the test comes back positive, given that the person actually has gunshot residue on their hand, or we can ask about the probability that the person has gunshot residue on their hand, given that the test is positive. one of the key takeaways for today is that those are different probabilities. Remember our very early discussion of conditional probability from an hour ago. The first term is the thing that we are assigning probability to. We are assigning here probability to the test outcome. And we are assuming something about the population that we're applying the test to. In this case, that they have gunshot residue. On the right-hand side, we're assigning probability to the true state of the world. Does the person have gunshot residue? And in this case, we're restricting attention to the set of tests where the answer came back positive. These are different probabilities. What do you want to know the probability about? What are you uncertain about? And what do you know for sure? In diagnostic testing like this, we can be sure we have data about how the test works. And so we have information about the probability the test. We want to know the opposite, and Bayes' theorem allows us to turn it around. There's only one challenge, which is to use Bayes' theorem and turn it around. We need some information that we may not know. It's known in the diagnostic world as the prevalence. It's sometimes also called prior information or outside information. We need to know how popular gunshot residue is, or how common gunshot residue is in the population of interest. And so let's see how this works. So here's how this might work for us. Suppose we buy a gunshot residue test. I work in a crime lab. I buy a gunshot residue test from the Acme Gunshot Residue Test Company. And they tell me, based on their lab research, that if you apply this to someone's hand who does have gunshot residue, the probability the test will come back is 98%. Sounds very, very good. The test is very sensitive. There will be many true positives. And they tell us, if you apply this test to someone whose hands are clean and pure, you should get a negative result 96% of the time. So the test also seems pretty good on this side. We would say the test is very specific. It has a low rate of false positives. And for now, I'm going to assume that I'm doing the test in an environment where gunshot residue is common. So let's just say we'll call it Wyoming, okay? A lot of people in Wyoming shoot guns for leisure, and so maybe it's not uncommon to find gunshot residue there. Now, in Wyoming, there's a criminal case. I bring in a suspect, I test them for gunshot residue, and I get back a positive test result. I'd like to know what I can say about the probability that this person actually has gunshot residue, given that the test says positive. Ordinarily, we'd say, hey, this is a good test, test positive, person must have gunshot residue. But one of the things I'm trying to convey today is there's always some uncertainty. The test is capable of error, and we should take account of that in drawing a conclusion. We can't rely on the test 100%. So there's a mathematical theorem that allows you to compute these probabilities. It is laid out on the slide for you to look at a later date. But the easier way to think about this for me is through what I would call a tree of probabilities. And so the way that we're going to walk through this is we're going to start on the left and imagine that we have 1,000 people from Wyoming. I've told you, I'm assuming that in Wyoming, gunshot residue is common, and that there's a 90% chance that the average person has gunshot residue on their hand. So in Wyoming, if I took 1,000 people from the population, and my assumption is true about the prevalence, 900 of those people would have gunshot residue, and 100 people would not. So that's really just an assumption on my part about the population I'm dealing with. And then the second part of the tree is uses what I know about the test from the manufacturer. So when I run this test on the 900 people who actually have gunshot residue, It's a very, very good test. 98% of them, 882 people, will test positive. And only 2% of those 900, which is 18 people, actually have gunshot residue, but will test negative by error. And I can also do the test on the 100 people who have no gunshot residue. And as we know, again, the test is accurate. So 96% of them will return a negative test. 4 of them will return a positive test in error. So now I'd like to find out, if I restrict attention to people whose tests are positive, how many of them actually have gunshot residue? Well, the test came back positive for 886 of those 1,000 people. 882 actually did have residue, 4 did not. And so we would say the probability that this individual has gunshot residue on their hands, given that their test came back positive, is 882 out of 886 such people, 99.5%. This matches our intuition. We have a very accurate test. When the test comes back positive, I, as a member of the jury, can feel confident that the person actually has gunshot residue. So this person fired a gun. That doesn't mean anything in the context of the case necessarily, right? We need to know that the person was in the place where the gun was fired, et cetera, right? But in terms of certainty about gunshot residue being present, we can be very confident. So let's think about that in a slightly different situation. So I'm going to show you something that I find surprising. You may or may not. Same exact setting, same exact test. So the test is still very good, 98% sensitivity, 96% specificity. It's almost always gives the right answer. But I'm going to apply the test in a different state. Let's call it, I don't know, Connecticut. Guns, people shooting guns is rarer in Connecticut. And so I'm just speculating that the prevalence of gunshot residue on an individual, a priori, without knowing anything else, is pretty low. It's about 5%. So we'll call this the low prevalence test. And based on this low prevalence situation, I'm going to ask you to think about Bayes' rule. And suppose the test comes back positive. How confident are you that this person has gunshot residue on their hand? And now, Kristen. Can we do the Zoom poll now? There you go. So we're going to go through it again, another tree, but I'm saying if I apply the test in a different environment, the same excellent test, what's the probability that the person actually has gunshot residue given that the test came back positive? I will share that this is actually a hard question. I ask you for your sense of it in part so that when we see the answer, you can see how your intuition matches up with the mathematics. And the drum roll. So many people are, sorry, the largest answer was 0.75. Excuse me, people are reasonably well spread out. Some people still believe the test is very, very, very accurate, and others begin to have less confidence in the result. I will note that many fewer people answered. That's unfortunate. It's all in good fun. We don't keep a record of your answer. So let's go forward and redo the tree. So now we have 1,000 people in Connecticut, and only 5% of them have gunshot residue, 50 people. The test is very accurate, 98% accurate. So 49 of them test positive, only 1 doesn't. But now there's a large number of people who don't have gunshot residue. And even though the test is quite accurate, 96%, the 4% false positives turn out to be a non-trivial number of people. 38 people are false positives, 912 are true negatives for these non-residue people. And so now when I focus in on the people who tested positive, there are 87 of them, only 49 has residue. So the probability that the person has gunshot residue given the test came back positive is only 56%. So it turns out that this other information, which we don't generally have, plays a key role. And I'll say quite a bit more about that in the remaining half hour. But what's important to note is I used gunshot residue. We talked a little bit about pregnancy tests, for example. Another place where this is interesting to think about is drug testing. Right? Suppose you work for a very, very large company and they say, we think we should have a drug testing policy. We want to know if people who work for our company are using drugs. So we're going to mandate drug testing. And there are places that do that. How does what we just learned apply? Again, no drug test is perfect. And so if there is some possibility of a false positive or some possibility of a false negative, we need to be concerned about the kinds of mathematics that we just talked about, and the prevalence will matter. And so if you do drug testing in a large company where there's reason to believe drug use is rare, because it is rare in the general population, you are in this situation that's shown right now. The false positive rate could be a problem. And so a good reason why this example, though a little sophisticated, is really important to understand that when we do the test, we need to take account of the uncertainty that comes from the fact that no test is perfect. What does this have to do with forensics? Well, here's a way of thinking about that. I'm going to change from the test, the diagnostic test world, to the courtroom for the moment and say, suppose I have some evidence E. These could be DNA markers, could be measurements on glass fragments, could be a blood stain pattern found at a crime scene. You are aware, all of you are aware of many, many examples. And when I analyze the data, I might have two propositions in mind. The same source proposition, the two samples came from the same source, or the different source proposition. Two samples have different sources. I've mentioned at the very beginning of today's short course session that we can assign probabilities to virtually anything. And so just as we had probabilities for the test and for whether the person had gunshot residue, I can apply that probability terminology here. And notice that there are two different ways of thinking about probability. The first bullet, where my hand is now, says we can ask about the probability of seeing evidence E if the suspect is the source of both samples. Or we can ask about what's the probability of seeing evidence like this if the suspect is not the source of the evidence. So the suspect sample and the crime scene sample have different sources. These are probability statements that are trying to assign probability to the evidence. How likely am I to see evidence like this in different situations? But we could have asked the opposite question. I've seen this evidence. What's the probability that the suspect is the source? Or I've seen this evidence. What's the probability the suspect is not the source? So just like we had two probabilities way back here, and they were not the same, I want to emphasize, sorry for giving people whiplash. that these two probabilities are not the same. Remember, key takeaway for today, how do we read conditional probability statements? We ask ourselves, what am I assigning probability to? I'm assigning probability to the evidence, to getting these DNA markers, to getting these glass measurements, to seeing these bullet cartridge case impressions. And I'm assuming certain information about the two samples. On the bottom of the slide, I'm assigning probabilities to the suspect, to whether this suspect is the source or not, based on what I've seen in the evidence. Only key point for now is these are different. It turns out that Bayes' rule allows us to think about them and how they are related to each other. And just like Bayes' rule allowed us to go from what we knew about the test based on lab studies to what we could learn about the individual from the test result, we can also use Bayes' theorem or Bayes' rule to, if you will, turn these probability statements around. And so what I have on the bottom here is a formula that turns out to be very important, that a lot of ongoing current conversations about how to think about evidence are based on understanding this formula. So we will talk about it briefly today and come back to it later in the short course. The part on the left-hand side talks about same source versus different source based on the evidence. And the parts on the right-hand side, there are actually two parts. The first part talks about the evidence given these two possible versions of the world. And the last part, the last term, talks about, if you will, the prevalence, the probability that this is of a same source case and the probability of a different source case. I see a couple of questions building up, but I want to go a few minutes more on this topic before I address them. So Bayes' theorem, I've reproduced here, is often described by mathematicians and statisticians in the following way. There are three ratios here. Remember, if you have one probability divided by another, we call those the odds. And so you actually have three such ratios here. The term on the far right is called the a priori, or before looking at the evidence. Notice that the evidence plays no part here. It's the a priori odds in favor of the same source proposition. The second term, the term in the middle, if you will, is known as the likelihood ratio. His likely ratio will come back later, as I said, but it is a statement about how likely you are to get the evidence. If it is same source, how likely are you to get the evidence if it's different source? And it looks at the ratio of those two probabilities. And what Bayes' rule tells us is if you multiply the prior odds times the likelihood ratio, you end up with what's known as the posterior odds. The posterior meaning after, in this case, after looking at the evidence. So after I look at the evidence, I can say now, I've updated my odds for the same source versus different source. As I said, we'll spend much more time on this with specific forensic examples. But for today, I only want you to be aware of the distinction between the posterior odds and the likelihood ratio, because they play a key role in the skipper key. So let's see what the questions that have come up are. Two comments. First, thank you from Ekram, who needs to leave early and missed the last half hour, but is enjoying it, and ask, will he be able to watch this later offline? I'm glad he asked, because that is another great question. You will be able to watch these later online. I think it takes us about a week to post, and hopefully I'll remember to tell you that next time when we get together. But we do post these after the fact. And Chris Pedersen asks, is this a form of bias? Since he asked it 4 minutes ago, I'm not exactly sure what he is referring to, but I think he's really talking about the potential for bias in choosing some of these probabilities, especially the one on the right. And so let's say a bit more about that in the context of the case. And if it's still unclear, Chris, you can ask me again towards the end. We should have some time for questions. So let me tell you how this Bayes' theorem and the likelihood ratio play out, first in the gunshot residue case and then in the Skipper paternity case. The way the likelihood ratio works out is, in the gunshot residue example, the evidence we could think about as being the test result. There are two scenarios. The suspect has gunshot residue, or the suspect does not have gunshot residue. The evidence, suppose the evidence result is a positive test outcome. The likelihood ratio is then defined as, hey, what's the probability I would get a positive test if the suspect actually has gunshot residue? And that's divided by the probability that the test comes back positive if the person doesn't have gunshot residue. Well, hopefully you remember when we laid this out, we know those probabilities. The lab, the manufacturer that created the test, did lab studies, told us those probabilities. So the likelihood ratio is 24.5 for a positive test. And the way that we can use that likelihood ratio is we can use it to update our prevalence. And the way this works, and I think when Chris asks, is this a form of bias, is if I were talking to a jury and trying to explain this, what I might say is, if before I testified, you thought 90% sure that the person had gunshot residue, then my 9 to 1, right? If those were your odds beforehand, my telling you that the test was positive provides a likelihood ratio of 24.5. You should multiply your prior odds, 9 to 1, by 24.5, and end up with posterior odds of 220 to 1, which maps back to the posterior probability that we saw. If, on the other hand, your prior odds, based on everything else you've heard in the case before I testify, is low, you think it's unlikely this person has gunshot residue. So your prior odds are 1 to 19. You think about a 5% chance or so. Then the posterior odds would get multiplied by 24.5, would become 24.5 to 19, which gives you a posterior probability of 0.56. So these two answers map back to the calculations we did on the trees, and they show that the likelihood ratio in this case is a fixed number. It's a property of the test. If the test comes back positive, the likelihood ratio is 24. The test result is 24 times more likely if you have gunshot residue than if you don't. To further interpret that requires some prior odds. Chris asked if that's a form of bias. I don't know that I would use that term, but it is true that it does give me concern about allowing that person's prior opinion to impact the conclusion that they would draw. There's a little footnote here that I won't spend time on, but in this case, the evidence could have turned out one of two ways. It could either have turned out with a positive test or a negative test. We've talked about the positive test in great detail, but the negative test can also, that could have been the outcome, and it would have made the evidence shift against gunshot residue, and the likelihood ratio would be 1/48 in that case. So as I said, much more on the likelihood ratio. We'll have a couple of hours on it the first week in November. So tell your friends, tell your family, come back for more on the likelihood ratio. But now to finish today's exciting episode, let's return to the case of the state of Connecticut versus Skipper. Remember, the expert witness testified that the paternity index was 3,496. It turns out that, and I should have said this, the expert comes from I forgot the name of the company. It's a famous genotype testing company. Shoot, forget the name of the company. Again, the company had done a lot of work in the lab. They knew the properties of the diagnostic test, and therefore they knew the likelihood ratio. They could tell that the probability of seeing mother, suspect, child, DNA profile, if the suspect was the father of the child, was 3,496 times larger than the probability of getting the same child's DNA profile from a mother and a random male. The expert said, you know what? You, the jury, really want to know what's the probability that he's the father. I can do that for you. I can tell you that given this paternity index, the probability this person is a father is 0.9997, 99.97% sure. Perhaps not surprisingly, given such testimony, Skipper was convicted. He filed an appeal claiming the statistical evidence was improperly admitted. That's a theme of the cases we're talking about. Not surprising, given that it's a workshop on statistics in the courts. So what do you think the court should do in this case? Let the conviction stand because the likelihood ratio is very high. Let the conviction stand because the probability that Skipper is the father is 0.9997. Overturn the conviction because there's no role for statistics in this case. Or overturn the conviction because the expert overstepped in creating a probability out of the likelihood ratio. So I will ask you again, I think this is the last Zoom poll of the day. Please participate. Answer. About half the people, a little less than half the people think the conviction should stand, some based on the likelihood ratio, some based on the posterior probability, and some think it should be overturned because the expert overstepped. Let's find out what the judge did and then what I think about what the judge did. Skipper was convicted. He filed an appeal. The state Supreme Court found that the expert's application of Bayes' theorem was inconsistent with the presumption of innocence and sent it back for a new trial. Once again, sometimes as a statistician, you get concerned about what judges and lawyers know about statistics, but once again, the judge acquitted him or herself well. The judge basically said, the only way that, well, you know, he didn't have to say this actually, the expert explained what the expert had done. The expert had assumed the prior probability of paternity was 50% and the prior probability of not paternity was 50%, and used that to go from the likelihood ratio to the posterior probability. And the judge found, assuming before you look at the evidence, that the person had a 50% chance of being the father violates the presumption of innocence. Interesting. For those old enough to know, it's like a Perry Mason moment. Dun, 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 dun. So how does this look in statistical terms? E here is the genetic evidence. I changed the hypotheses. So HD is that the defendant is the father. HR is that the random man is the father. And the way Bayes' theorem looks in this case is we can start with the expert testified about the term in the middle. The company's software allows you to compute what's the probability of seeing evidence like this if the defendant is the father. If a random man is the father. And that likelihood ratio, that middle term, was 34.96. To turn it into a probability that the defendant is the father, as the expert wanted to do, and indeed as the expert did, you need to have prior odds. So the expert, and it's interesting, people frequently do this. They say, oh, look, there's only two outcomes. Either the defendant is the father or the random man is the father. So we'll just say they're equally likely. Why not? 50-50. And when you do that, you get 50-50, or a ratio of 1, gets multiplied by the likelihood ratio of 34.96, which says the posterior odds are 34.96 to 1. And if you go back way back to the beginning, to slide whatever it is, 4, 5, 6, 7, 8, which relates probabilities and odds, it turns out that you can take those odds and turn them into a probability, as the expert did, and get 0.9997. So this is where we make the connection that to do what the expert did, you need to make some assumption about the probability the defendant is the father. Once again, in this case, the two ways of thinking about probability are understanding the difference between the two ways of thinking about probability is key. There is a huge difference between making a statement about the probability of the evidence given or conditional on some assumption about the state of the world, the truth, ground truth. And there's a big difference between that probability to assigning probabilities to states of the world, to telling people which state of the world is more likely based on looking at the evidence. What makes forensic science and statistics a challenging pair is it seems obvious that we desperately want to know what's the probability that this man is the father after we've looked at the evidence. I think we all agree on that. We want this quantity. But what I am hoping I conveyed today, and will try to convey again later in the short course, is to get that answer out. There is no other way. It is required that you must have had somewhere in the back of your head a pre-evidence probability that the defendant is the father. The court here found that it's not appropriate for the forensic expert to have that opinion, that evidence was prejudicial. It's kind of interesting because on the one hand, you might say, maybe the judge is arguing 50% is prejudicial. Could it be 40% probability? Could it be 10% probability? Any percent probability, though, is prejudicial by the judge's ruling, and that seems insane. But I think what the judge is really saying, or at least what I would say, is given the challenge associated with assuming a priori whether this man is the father or not, that the forensic expert should stick to what they know, which is what's been shown in the lab about the genetic test. And that is the likelihood ratio in this case. And so we should be comfortable making statements about the probability of seeing the evidence based on experience in cases with known match or known non-match. And over the next 3 weeks, we'll talk about different ways of assessing forensic evidence. And I think they all do have in mind the notion that we should think about how likely is it to get evidence like this for same source pairs, and how likely is it to get evidence like this for different source pairs, and we should compare those two things. So let me wrap up. We'll have 5 to 10 minutes for questions, and there's one question already in there. I do encourage you to put in questions. Here's my summary of the 2 hours we've had together. First, about probability. Probability is the mathematical language of uncertainty, provides a common scale for talking about the chance that event occurs that applies to anything we might think about. The weather, the outcome of an election, the outcome of sporting events. I've argued that conditional probability is really the very key concept. In fact, I usually tell people all probability is conditional. It depends on what information you are assuming about the population. We saw that independent events can be very powerful in the case they allow us to multiply probabilities, but we need to be careful. And we saw Bayes' rule as a mathematical result that allows us to update probabilities in the face of evidence, go from prior probabilities through evidence to posterior probabilities. What do I hope you take away from this? When probability is coming up in a forensic setting, we should think about what is the basis for the probabilities? What is the evidence? That was lacking in the Collins case, but we have it when we do diagnostic tests. We know how those tests work based on laboratory studies. We should recognize that the assumption of independence is very, very powerful, but that it needs to be confirmed, that it's not true just because you say it. There was a case that had some fame attached to it in which a video of a person committing a crime showed a particular shirt. They found a shirt matching the pattern in the suspect's home, and they compared the shirts, and they saw different features of the shirt, and they argued they're independent, but maybe true, maybe not true. And the last thing we noticed today is probability statements need to be very carefully interpreted. To what event are we assigning probabilities? What information are we assuming to be true? And in forensics, that shows up most often in the distinction between trying to talk about the probability of evidence arising, particular measurements arising, given different assumptions about the state of the world, gets contrasted with making statements about the hypothesis or about a proposition or about a state of the world. So I will stop there. That is the final slide of part one. An anonymous attendee says that I may not know, but that accrediting bodies have established that the presumption of 50-50 a priori odds is the standard currently being used for paternity. I do not know that. I should have given this disclaimer at the start of the whole session. I am a statistician. I have been engaged in conversations with forensic scientists for almost 25 years at this point. So I know a fair bit, but I am not a forensic practitioner. I have never worked on or testified in a paternity case. So thank you for sharing that. I do think, that for the work that I've done in pattern evidence and otherwise, I think the judge in the Skipper case was right, and that we don't really need to do the posterior probability, that the likelihood ratio is the key summary of the evidence. So let me stop there. There's still 5 minutes left in our allotted time. So if people have questions, please type them in. One of my concerns has always been, I usually talk right up to the very last minute, and then there's no opportunity for questions. You did a great job of putting questions in during the 2 hours, but we do have time. So there are no bad questions. You can always ask them anonymously. A reminder, there are 3 more sessions to this short course. Next Friday, part 2, we'll talk about reliability, collecting data, reliability of data, and some of the considerations that go into black box studies. In 2 weeks, on October 25th, we will talk about more formal statistics, hypothesis tests, and how they're used in forensics. And then in 3 weeks, on November 4th, the not to be missed exciting conclusion, a discussion of the likelihood ratio. Sue asked, are there any cases that have been accepted in the courtroom using the mentioned methods? Any high profile cases? What I would say is, it turns out, not to be super easy to find lots and lots of cases with probability in them, but the probabilistic reasoning is hugely impactful in DNA testing. So it shows up in DNA case all the time, including the infamous or famous O.J. Simpson case. And so the laws of probability show up all the time, but usually probability is really just a building block for the arguments that are being made in court. And what really shows up are the methods that you'll see in the remaining sessions 2, 3, and 4 of the course. To those thanking me, I thank you for being here. It's really the kind of work that we're at CSAFE trying to do to work with the community. So please tell your friends. We will post this one, and we welcome more people. If they have not yet registered, they should still be able to register and join us for the next 3 weeks. If we're online, the more the better. And thanks for all the questions. And I look forward to working with many of you again next Friday.
Hal, thank you so much for being here today and for sharing your wisdom with us. I think this is a great setup for the remaining 3 sessions of this short course. This is a good pace. Thank you all for joining us. We hope you have a great day.